So in this lecture, we will talk about the Prandtl's finite wing lifting theory. The idea is not to do the full derivation, but to give highlights of the major topics. And this summarizes everything that we have learned so far. So one of the things is consider a flat panel, okay? And what you know here, for what we have spoken before, that your circulation around the tips, right? This circulation here and the total circulation here is going to be completely equal to zero. That's what this is saying, okay? Because the circulation is equal to zero, then as a default, your lift has to be zero at the tips. Okay, so that's something that's a direct consequence of this. Now, we also, what we're going to do is we're going to say that it's possible to have your lift can be a function of the value of your circulation. Okay, so if that was the case, then everything I know, if I know a circulation value, I can say this is directly dependent on the lift. Okay, and then the lift it's not zero everywhere else, so the lift is zero here because the circulation is zero there. So that just tells you that directly the proportional. So this is zero here because this is zero there. But nothing can be say anywhere in between that. Your circulation, the value of circulation is not zero, and therefore your lift is not zero. Okay, so if I take a side view on the loop, okay, around on the ends, only at the ends, as I told you here, okay, only at the ends. So what we do here typically is we go from here, b over 2 and minus b over 2, where the whole thing is b, that's the span. We talked about this before. So this is true, is zero at is zero, I call this y, so it's zero at y equal to b over 2 and minus b over 2 only, okay? So if you think about a finite body and you have a flow that's going around this, what you're going to see is the flow, it's going to create some vortices lines, right? The vortices that come here around this. And that's actually the whole idea here. That's what happens because of this thin wall. We know that circulation is there, but there's a circulation happening here as the flow comes in this direction. Circulation is going in this direction, and so therefore it will continue in the same direction on both sides. And here it will also continue in the opposite direction. Okay, so you can see that that's what's happening here. This will be also the same value as this. So if you look at this, they have a circulation in each one of the points, and this becomes like a vortex filament, if you would, right? And so if you just move on now, what you really have is one of the things to keep in mind, that the circulation around any loop that is equal to the vorticity across the surface bound by that loop itself. The vortex lines cannot end in a flow. These are actually consequences of the Helmholtz vortex principle. Circulation around the vortex line does not change. So therefore, in this particular line, this vortex sheet, if you would, you're saying the circulation has to be completely same all the way through, okay? The circulation around the various section may differ. So if I have a circulation in a different section, that may have a different value than this. So as the result of this, these are vortex sheets, and each one of the vortex sheets can have their own circulation. So call this sigma gamma 1, gamma 2, and gamma 3, and that's going to be different. That's going to have a consequence on the value of the circulation across these lines. And we're going to look at that for a moment. And then what happens typically is the vortex lines, if this is going in this direction, the other one is going to go in the opposite direction. And the reason behind this is going like this, but when you move here, this is moving like this, And remember, just think about, you take this sheet and you turn it at 90 degrees and you turn it at 90 degrees again. So this is going like this, and then this is going like this, and you turn it 90 degrees again. Now it's actually end up in the opposite direction. Okay, so that's why these two will always be in the opposite direction. They are opposites. Okay, so one of the things is, what happens is you have infinite number of these vortex lines here, because this is actually a sheet. That's what's going to happen. Remember, this model's a wing. Okay, this is a wing, a flat wing, because it's a thin wall airfoil. Okay, so, and this is bound by many vortices, which are actually responsible to create the lift. Remember how we started the discussion, that if I have a circulation, it's only then that will have I'm going to have lift. If I don't have lift circulation, I cannot have lift. Okay, so with that said, there's no pressure across the vortices, so the pressure difference between each one of the vortex lines does not change. The pressure jump across the vortices is what actually provides the lift itself, because that also depends on that. Now, what we call this is something we call horseshoe vortices. When we say horseshoe vortices, what we are saying is, as I just mentioned, this is a sheet, right? And this is a complete sheet, and it's going to have, it could have a probably infinite number of vortex lines. And each one of them, you can see, is going to come here. And this is a line, it's called the lifting line. This is the lifting line. So what we are saying is that your entire lifting line, that your entire airfoil can be modeled at that line, and where that line is located at your aerodynamic center. Okay, so you have basically all this airfoil, all these values are actually going across this. Okay, they come here, they go there, they come here, they go there. And basically what's happening here is, you can see that each one of them is going to have a different value. And this horseshoe basically saying is, if I have a value here, the amount of lift happening here is going to depend on this value here. And then once I come here, now I have a different value, so therefore I'm going to keep adding that up, and this is what I get. Eventually, if you have an infinite number of them, and I'm going to go ahead of myself, what's going to happen is you're going to have a nice parabolic equation or something similar to that. Okay, so one of the things that lifting line approximation is nothing else than, you take your airfoil. Remember, this is my wing, the wing of your airplane, right? And I'm just drawing half of this, right? Because the total B is, just think that you have the airfoil right here, okay? So this is the wing, and this is the total wingspan of that, and this is the chord of the airfoil, and assumes that's constant. So for airfoil ratios that bigger, way bigger than 1, that can be represented as safely as like a straight line. So that's what we did here, right? Assumed everything was a straight line. That's what we call a lifting line approximation. Okay, and then lifting line approximation, you can see that I'm going to have circulation 1, 1, I have 2, 2, 3, then I have 3, and so on and so forth. They go in pairs in opposite directions. And you can see that happens at the aerodynamic center. And the aerodynamic center for a thin wall airfoil is C/4. Okay. So the infinite number of lines I just mentioned, what we call these horseshoes, will give you something that looks like this. That's what you end up with. Okay. So the consequence of having these vortices here at the tip are the ones that are responsible for the induced velocity. Induced velocity Induced velocity is nothing else than what we call a downwash velocity, and we just talked about this in the previous couple of classes back, where we are saying there's an extra amount of lift that's actually created that. And if you wanted to know how much is that value, and we'll do a homework on that, if I want to know how much is that velocity in which this is pulling down here, I can use Biot-Savart principle, and I can go from here to there, and I can calculate that value. Okay, and that's what's going to happen here. Okay, and then here this goes to infinite, okay, infinity, and that could also have an influence, and we could talk about that as well. So if you consider the horse, what we call the horseshoe, this is a one word, the horseshoe, and we want to find the downward velocity, let's say at this location. So this is kind of what it's going to really look like, and this profile is going to change as I move away from the aircraft, and that actually pushes the aircraft down, which you cannot avoid. You want to try to minimize it, but you're always going to have this because you just have lift. Okay, because you have circulation, you will have this. Impossible to eliminate that. With that said, so let's consider a case where I have induced velocity. So that extra velocity here, that's the velocity I'm talking here, right there. Okay, so this is my total velocity, what I'm calling the velocity Q. Okay, so if I said that velocity, where was I? So I'm saying that Q, okay, and I call W that downward velocity, that's minus K. This is the downwash speed, okay, and plus your V infinite, that's actually depend on the axis I use here. Okay, so here I'm using the value. If this is X, then it's I. If it's J, then this is J. And then if I have no U component or V component, if I do it like that, then you can know that this is way bigger than Q. A consequence of this would be the resultant velocity would be your V infinite plus Q. Remember, this is the influence of the downward velocity itself. So we know that the vertical velocity is going to be bigger than the horizontal velocity. So therefore, this whole thing is actually equal to this. This is what it actually ends up being like at the end of the day. So once this is done, then what you're going to have is, we know that the airfoil width, we take what we call a slice theory. So I can take this sheet, and I can take a small slice. So I take a slice here and here and call it dy. Okay, so this is the value, this is the dy width that we are talking about in the airfoil. So as we move on, and I take the slice and I'm moving, and I have a circulation around that. What you can know here immediately, you're going to have, if I didn't have the induced velocity, I'm going to have this purely. But because now I have an extra velocity that's pushing my aircraft back, and what's responsible for that is my downward velocity, then downwash velocity, then I'm going to have a drag component that shows up. So how to find those components, we're going to use what we call Jokowski Theorem. We talked about that already in the last topic. And we know that that's equal to this. So you can go back and review what was actually these equations. And remember that anytime I have this bar, this is nothing else that's minus gamma. It's just saying that the rotation is going in the opposite direction. So for a two-dimensional airfoil theory, what you're going to have is, this is the zero lifting line. It's the location where your angle of attack is completely zero, or this is the camber line, if you would. Okay, then you have the stream velocity, so this whole thing is the angle of attack, but then you have a resultant velocity, because then you're going to have a you will have a induced angle of attack, because of the downwash velocity. Okay, so this is what's responsible for that is the downwash. That's what's creating this induced angle of attack. And that induced angle of attack is going to actually reduce your effective total angle of attack, which will be alpha minus alpha I. Okay? So in this location right here, if I did that, you're going to see you're going to have an extra component there. That's where that component comes from. And this is equal to this. And typically your induced angle is very, very small. So therefore this is equal to this. You can say these are very close to each other. That's a very good approximation. There are cases in which you may want to calculate that exactly. Then if I just find my variation of my total force with the variation of my lift, and if you remember, I told you the lift is going to be a function of your circulation as well. So your force is equal to this, right? And I can go ahead and solve for my circulation. That's exactly what I did here. There's a delta missing there. So this is equal to this. And this right here, if I divide this side and I find the divide this v squared 1/2 of s, s is equal to this, then you can show that your angle, your coefficient of angle of attack is equal to this nice equation right here. Okay, so your total circulation, then once you replace everything, you can show your circulation is nothing else than the value for circulation would be a function of y is 1/2 to your resultant velocity times, this is a function of y. If it's a straight line, there is a constant, and this is your lift coefficient, CL. Okay, so if I had that, then I could find what my lift is, and we're going to get there in a minute. C over L, we know is actually leaves you to the delta C over L, delta over the angle of attack, or effective angle of attack gives you this, where I could use, your CL is, if you remember, using Taylor series expansion, you can, for a linear approximation, this is equal to this. So this is nothing else than what we call A sub 0. A sub 0 is equal to this, and we learned this a couple of classes back. Where you just say, what is the slope of this when my effective angle is actually 0? Typical value for thin wall airfoil structures, this is equal to 2 pi, but it has to be calculated, and we learned how to do that previously. So usually we can express K in terms of these values right here. Okay, so your entire expression here, if you would, K is what you call a shape function, shape form parameter, and you could approximate this using, you could have equivalency between these two as follows. Okay. So just to summarize a few things, this is the angle of attack, this is the induced angle of attack. We will work with each one of these components in the next couple of charts. But this is giving you a general overview of this, and so the total angle of attack is equal to the summation of that. And what we really need in the airfoil is the effective. So what I did in the previous charts, I call this R. So this will be alpha minus the induced angle. Okay, so, and this is the addition of that. So if you wanted to know what your effective was, then that will actually come on the other side, or you could, if you had enough information, you could find this. So if I knew my angles of attack, I could bring this on this side, and I could solve for this, and I could backtrack what my course should be, or my or any of these design parameters should be. Okay, so again, this is one more time here coming to do this derivation. So if I'm going to find this is actually a tangent of this value, is opposite of an adjacent value. For a very small angle, as we said, and this is actually approximately equal to this. One of the things you want to keep in mind, if this is actually, this is the value of alpha is less than naught, your wing could be twisted, so that's what this means, but it's very slightly, very small. So the downwash velocity is caused by vortices, as we spoke. For a to the rotational flow due to vortex, we know that this equation is true. We derived this many lectures back. This is to the pure vortex. The Pius-Bart law actually gives you this, and also another, and we only worked with a couple of examples, so we kind of know how to work with this. Now in an infinite segment, if you have an infinite segment, then you have this. This gives you exactly the same result that you got here. Pius-Bart's law says that if I have this line here, and you have this rotation, I want to know what my velocity is at any point, let's say this point, or this point, let's say I want to find this point, then I just have the dimension, I got the angles, and I can find what I was looking for. What you want to do for the downward velocity, you solve for that. This is just a simple substitution of what we know everything is, because we know that this is nothing else than gamma. So if I take the derivative of this, and this is a function of that, then you know this is actually, you take the differential of that, this will give you nothing else difference in dy, because this is a function of y itself. So if I wanted to know in the vortex sheets what is that value for each one of those values, I can plug inside this equation, and I'm going to just jump into the equation here. You have to take a good set of notes here, but I just want to go to the final answer, what I really care for. What is very important is this value here, where eta is nothing else than that is the value due to the vorticity. Okay, so we know that your circulation has to be bigger than 0 for every y bigger than 0. The total circulation then is actually given by this equation right here. And so if I keep doing some mathematic manipulation here, this is where I found this, the values here, and you can do this derivatives like we have done before. We know the tip this is equal to 0. We know that the lift and drag, they're perpendicular to, they're not necessarily perpendicular to each other, but they are perpendicular to the force, and drag is parallel to the force. So at the end of the day, your lift is going to actually equal to this, and your drag is going to equal to this. And we can find there's some nice closed form solutions that are actually equal to these nice equations right here. Okay, so if we know all those values, then we can find what your lift and your drag are in the equation. If they're constant, they look something like this. And so the problem reduces in 3 parts. First of all, you could know what your circulation is, and if you know your circulation, we want to find the downwash velocity, your angle of attack, we want to find your chord, and we want to find your A sub 0. A sub 0, remember, this is nothing else than CL is equal to A sub 0 times your angle of attack, okay? Then second problem could be, I got my angle of attack, I have my chord, I have A sub 0, and I want to find the circulation and the downwash velocity. The third one could be, we want to optimize the whole problem to minimize the induced drag. So these are 3 types of problems that we typically want to do. So the best way to do this is in the next topic, we are going to apply all this to elliptic wing that will help us to better understand these concepts.